yesterday. So remember, you kind of reviewed, you graphed a parent function, exponential function. Okay. So that was like something we were used to. We knew where the asymptote was. We plugged in to make a table. Then what we said is that log functions are the inverses of exponential functions. So what did we remember about inverse functions? What are some of their characteristics? Good. So our inputs and outputs kind of switch. So x's become y's, y's become x's. So we see that in the table here. Savannah? Good. And our asymptote is going to be at x equals 0. So when we go to put that on the graph, let's think about what this is going to look like. So x equals 0 is what kind of line? Yeah, so Jordan's going like this, Kenny's going like this, right? It's a vertical line, if I could say it. So this is our asymptote for our log function. And if you went and you physically went to plot these points, okay, 1/8, comma, -3. So 1/8 is really close to 0, comma, -3. So something way over here. Okay. And then 1/4, comma, -2. So that's like somewhere right there. And then 1/2, -1. There. And then 0, 1. Sorry, not 0, 1. 1, 0. I didn't switch it. No good. 1, 0. And then we have the point 2, 1. And then 4, 2. And 8, 3. So the curve is going to look like this. And then visually on the graph, do these look like inverses? Okay, so what makes them look like inverses? What were properties of inverses we knew from before graphically? Samantha? Good, y equals x. Okay, so y equals x is the line that you would reflect over to see the inverse. Do you see how those would be inverses? Okay, they kind of fit the idea. So now the question is going to be, how can we always go through and graph some of these log functions? Okay, so just like we graphed exponential functions, you're going to have people that eventually are going to give you problems that look, say, like this. Okay. And your job is going to be able to take the parent function, know what it looks like, and then do all the stretches, compressions, reflections, and shifting to get the new graph. Okay? So tonight in the video notes, we'll do a couple of those. Your video notes is like 8 minutes, something long. It's like 2 examples of graphing the parent function and then getting through the transformations. Our goal when you leave class today is to have a decent understanding of what you expect to see on the video notes for the parent functions. Okay? So we're going to summarize some stuff for ourselves that we expect to see each time we graph one of these log parent functions. And then we'll talk a little bit about the transformations, and you'll see them tonight. So the parent log function is the log function without any transformations. So it looks like this. The base is not a transformation. Okay? Just like with the exponential functions, how many parent functions are there with exponential functions? How many parent functions are there? Infinitely many, because the base can change, right? But with quadratics, how many parent functions was there? 1, x squared. Okay? But now because the x is in the exponent, you have this other thing that could change the base. So each time we start, there are some things that are the same, but depending on that base, our parent function changes. So same thing with log functions, because they live in this world of exponents. They're really another way to say exponential things. There are infinitely many parent functions because the base could change. And so you guys just saw that in general, the log graph looked like this. We had an asymptote here. And all of our parent functions will have that asymptote there at x equals 0. Okay. The reason is, remember in the definition of a logarithm, it said you take the logarithm with a base of a number x, and what had to be true about that number x? Had to be positive, okay, greater than 0. The base also had to be bigger than 0 but not equal to 1, but this number had to just be positive, okay? So that's why in the parent function there's nothing graphed from 0 over. Okay, the number had to be a positive number, okay, something more than 0. What other point will every log function have? You guys kind of figured it out when you were playing war, okay? What was the worst card to have when you were playing logarithm war? 0. And when did it always end up being 0? When you were taking the log with any base of 1. So whenever somebody plugs in 1 for x, no matter what the base is, they're going to get 0 for y. So what point is always going to exist in our logarithmic function graphs? 1, 0 in every parent graph, just like 0, 1 showed up in every exponential graph. Okay? So we have this point at 1, 0. And then you guys saw the shape that went like this. Now this would depend highly on the base. Okay? If the base of this log was 2, numbers I would probably like to plug in are 2. Because what's log base 2 of 2? 1. Okay? And if I wanted a point on the other side of this 1, 0, probably the other thing to plug in that would be good would be 1/2. Specifically because it's the reciprocal of 2. Because what is log base 2 of 1/2? -1. So I'm basically picking the numbers to plug in that give me 1 and -1. So I'm usually picking the base and the reciprocal of the base to plug in. Okay? Now, just like with exponential functions, there was growth and there was decay. When was there growth? What was considered exponential growth? What had to be true about the base? Ashley? Okay, it wasn't a fraction. Be a little more specific because 4 over 3 is a fraction, but that would still be exponential growth if that was raised to a power. Go ahead. It was greater than 1. This shape of our logarithmic graphs is when 1. Oops. 0. Okay. However, the shape could be slightly different. It's still going to possess those same two qualities, just like exponential growth and decay had the same asymptote and this one point that always stayed the same. But when the base is less than 1, okay, you're going to see the curve go like this. And here's why. Let's say that the base was 1/2. Okay? So you get your point, 1, 0. With a base of 1/2, I would probably choose to plug in 1/2 and 2. Okay, the number itself and the reciprocal, I think those will be easy logs to calculate. So let's think in our heads if I did that. If I plugged in 1/2, what is log base 1/2 of 1/2? 1. So 1/2 comma 1. Okay? But if I plug in 2, what is log base 1/2 of 2? -1 because 2 is the reciprocal of 1/2. Okay, so 2, -1. All right? So that's why you see the curve kind of change and grow here instead of here because of what would be the reciprocal. Do you see how I'm choosing the numbers that I would plug in to get the parent function graph? I'm specifically choosing the base and the reciprocal of the base, and here the output is always 1, and here the output is always -1. That makes it easy for me to graph. Okay? So your homework tonight is the video notes. And you're just going to see, it's going to be 2 examples like this. We graph the parent function, so we'll talk about good points to pick there. And then we'll write down the transformations, and we'll transform it to get the new graph. Very similar to exponential functions, except for that everything is the inverse, okay? So just a little bit kind of changing your perspective.